In this lesson, I will work 8 problems. The first 4 problems will be equations in quadratic form, and the second 4 problems will be higher degree equations. From our previous lesson on solving equations in quadratic form by substitution, we learned to recognize equations that can be converted to quadratic form. However, very often these equations can be solved by factoring. So in this lesson, I want us to work some of the very same problems that we worked in the lesson on solving equations in quadratic form, but I'd like for us to solve them by factoring instead of substitution. I'd like to begin by reviewing what we mean by an equation in quadratic form. Any equation that can be converted to the form AW squared plus BW plus C equals 0, where A, B, and C are real numbers and A does not equal to 0, is called an equation in quadratic form. Remember that A represents the coefficient of the squared term, B represents the coefficient of the linear term, and C is the constant. When we say A does not equal to 0, that means that we will have the quadratic term. For an equation to be an equation in quadratic form, it must have the quadratic term. It may also have the linear term and the constant term. When equations are equations in quadratic form, very often they can be factored, just like quadratic equations very often can be factored. So I'd like for us to look at some equations in quadratic form that we can factor to solve. In problem number 1, we have x to the 4th minus 5x squared plus 4 equals 0. We have a trinomial, don't we? We have 3 terms on the left, and of course when we say it's a trinomial, that means that the powers of x must be whole number powers. We learned how to factor this trinomial, didn't we? We know that first we look for common factor, and there's not one. Next, we know that for a trinomial, if it factors into 2 factors. We know that this first term times this first term must give us x to the 4th. In this case, we'll use x squared times x squared. I think it's important for us to realize here that this middle term variable expression, we are going to use this middle term variable expression times itself for our factors of the variable expression in our first term. We have to do that to ensure that we get the correct middle term. Now, we know that x squared times x squared gives us x to the 4th. To determine what these terms are, we go to the last term in our quadratic, the positive 4. Since it's positive, we know we want to find the factors of 4 whose sum will give us this number 5. Also, since it's positive, we know that our factors will have the same sign. When our factors have the same sign, that sign is determined by this middle sign. Since the middle sign is negative, then we know our factors will both have negative signs. Now, for our factors of 4, we could consider 1 times 4 and 2 times 2. And of course, the 1 times 4 gives us a sum of 5. So our factors will be minus 1, minus 4. And of course, we know that we can FOIL this out to check it, and let's do that. X squared times x squared gives us that x to the 4th. Our outside product, x squared times negative 4, gives us negative 4x squared. Notice that this variable expression has got to be the same as that variable expression. Our inside product, negative 1 times x squared, would give us negative 1x squared. Of course, these are like terms, so we add them up, and sure enough, when we do, we get minus 5x squared. And once again, that when I multiply this negative 1 times x squared, the variable expression needs to be the same as this variable expression so that I can add these two products to get this middle term. Last, negative 1 times negative 4 gives us a positive 4. So we have taken the left side of this equation in quadratic form and we have factored it. Of course, we realize it's an equation in quadratic form because if we take the variable expression of the middle term x squared and square it, we get the variable expression of the first term, and of course our three terms on the left are set equal to 0. Now, since we have factored the left side of this equation, we may use the zero product theorem that says if this factor times this factor equals 0, then x squared minus 1 must equal to 0, or x squared minus 4 must equal to 0. Solving this first equation, it is a quadratic equation. It does factor. It is the difference of squares. It factors as x plus 1 times x minus 1 equals 0. Once again, using our zero product theorem, we know that x plus 1 equals 0, or x minus 1 equals 0. Solving this first equation, let's subtract 1 from both sides. We get x equals negative 1. And for this second equation, let's add 1 to both sides. We get x equals 1. Moving on to our second quadratic equation, x squared minus 4 equals 0. It also factors. It is the difference of squares. It factors as x plus 2 times x minus 2. Using the zero product theorem and setting each factor equal to 0. Solving each of these equations, let's subtract 2 and then let's add 2. So we get 4 solutions, negative 1, 1, negative 2, and 2. Let's write those solutions using solution set notation. Let's write the negative 1 and 1 as plus or minus 1, and the negative 2 and 2 as plus or minus 2. I will leave the check of these solutions to you. We will look at 3 more equations in quadratic form, and you will see how we can factor them to solve them. Let's look at problem number 2. We have 4x minus the square root of x minus 3 equals 0. For quadratic form, of course, it is set equal to 0, but let's take this variable part of this middle term and let's square it. And, of course, the square root of x squared gives us x, and that is the variable part of this first term, so it is an equation in quadratic form. What's important about that is we know that we can take this x and we can express it as the square root of x squared. And of course we can express the square root of x squared as the square root of x times the square root of x. That's what we mean by the square root of x squared. So if we want to factor the left side of this equation, of course we look for common factor first, and there is not one. We know that this term times this term has got to give us the 4x. So how could we factor the 4x? Well, for the x part, we're going to use the square root of x times the square root of x. So now the question is, how do we factor 4? Well, we could say 2 times the square root of x times 2 times the square root of x, couldn't we? 2 times 2 will give us 4, and the square root of x times the square root of x gives us the x. The other way that we could factor this 4x would be to say 4 times the square root of x times 1 times the square root of x, and I don't need the 1. Once again, the square root of x times the square root of x gives us the x, and then times the 4 would give us the 4x. So one of these factorizations will be used for our first terms in our factors. To determine the factors of the minus 3, we have choices of 1 times negative 3 or negative 1 times 3. Since the sign is negative, we know that the signs of our factors will have to be different. Now, this is what we call trial and error method for factoring. Now, of course, this is not a trinomial because of the square root of x keeps this expression from being a polynomial. That power on x is actually x to the 1/2. We know that the square root of x means x to the 1/2, and 1/2 is not a whole number, and we know that polynomials have to have whole number powers. But we can use our trinomial factoring methods. So the choice here is, do I use 2 times the square root of x times 2 times the square root of x, or 4 times the square root of x times the square root of x? It would appear to me that probably I need to use the 4 times the square root of x times the square root of x, and then on the 3 and the 1, the 3 needs to go with the 4, and the 1 needs to go with the square root of x. That will give me an outside product of 4 times the square root of x and an inside product of 3 times the square root of x. Since the coefficient of my middle term is negative 1, then that tells me that the 4 needs to be negative and the 3 needs to be positive. Now let's check this. We'll have 4 times the square root of x times the square root of x, which would be 4x. That's that first term. For an outside product, 4 times the square root of x times negative 1 would be negative 4 times the square root of x. For an inside product, 3 times the square root of x would be positive 3 times the square root of x. When I add those together, notice that my radicals are like, so I can add the coefficients. Negative 4 plus 3 is negative 1 times the square root of x, which gives me the correct middle term, and then 3 times negative 1 gives me a negative 3. Notice that it is very important that I take this variable part of this middle term and multiply it times itself to get the variable part of the first term. That ensures that when I find my outside product and my inside product, that I have like terms that I can combine to give me this middle term. Now that I have this factored, let's use our zero product theorem. We may say 4 times the square root of x plus 3 equals 0, or the square root of x minus 1 equals 0. For this first equation, it's a radical equation. I know that I want to isolate the radical. I subtract 3 first. I'll have 4 times the square root of x equals negative 3. Let's divide both sides by 4. I get the square root of x equals negative 3/4. And of course, we know that if I have the square root of a real number, there's no way that I can get a negative result. So I get no solution from this equation. Let's work with this second equation. Once again, it's a radical equation. I want to isolate the radical. Let's add 1 to both sides. we'll get the square root of x is equal to 1. Next, I want to remove the radical. Since it is a square root, to remove the radical, I square both sides. The square root of x squared is x, so I get x equals 1. Now, since I did square both sides, I can introduce extraneous solution. So let's go back up to this equation, the equation I started with before I squared both sides, and see if this is a solution of that equation. If I replace this x with 1, I will have the square root of 1 minus 1. Does that equal to 0? Well, of course, the square root of 1 is 1. So I have 1 minus 1 equals 0. So it does check. So this is a solution of this original equation. I will leave the check to you. Now, on problem number 3, first let's check this middle term. Let's take x to the negative first and square it. And sure enough, we get x to the negative second. So my variable expressions verify that this is in quadratic form. And since the left side is equal to 0, this will be an equation in quadratic form. What I need to know is, well, how can I factor this x to the negative second? Well, since it's x to the negative first squared, and I know that when I square something, that just means to multiply it times itself, I will take this x to the negative second and factor it as x to the negative first times x to the negative first. Now, since I have a coefficient of 3, I will write this factorization. For my factors of 3, I'll use 1 times 3. So I'll write the factorization of this first term as 3x to the negative first times 1x to the negative first, and check it. X to the negative first times x to the negative first gives me that x to the negative second. On the positive 2, I don't really have a lot of choices here. Since it's positive, I know that the signs of both my factors will be the same. And of course, we go to this middle term to determine that sign when this third term is positive. Since the second term is negative, that tells me that I will use negative 1 times negative 2. So when I get ready to factor the left side of this equation, of course I look for common factors first, and there aren't any. My choices for first terms here then would be 3x to the negative 1 and x to the negative 1. And my choices for second terms would be negative 1 and negative 2. And it's just figuring out where the negative 1 and where the negative 2 will go. I believe if I put the negative 1 there and the negative 2 there, I will, when I will get the correct expression on the left side. Let's check it. 3x to the negative 1 times x to the negative 1 would be 3x. Remember, when we multiply like basis, we add the exponents. Negative 1 plus negative 1 would be negative 2. So that works. For an outside product, let's say the 3 times the negative 2 is negative 6, and then, of course, times the variable part, x to the negative 1. For an inside product, negative 1 times x to the negative 1 would be negative 1 x to the negative 1. If I combine these, and I may combine these because the variable part's the same, I say negative 6 plus negative 1 gives me negative 7, and of course the variable part stays the same. Notice once again how important it is that I take the variable part of this middle term and multiply it times itself for the factorization of this first term, so that when I have outside product and inside product, that the variable part of those terms is equal to that variable part of that middle term. Let's check last term. Negative 1 times negative 2 gives me a positive 2. Now I may use my zero product theorem. I may say 3x to the negative 1, subtract 1 equals 0, or x to the negative 1 minus 2 equals 0. Now, there's several ways that I can work this. So to begin with, I know that the x to the negative 1 needs to be rewritten. Since x to the negative 1 is a factor of this first term, I may write the x in the denominator to the positive 1 power by definition. Remember that the negative 1 does not apply to the 3. If it applied to the 3, then that 3x would have to be in parentheses. Now I have a fractional equation here, so what I want to do is to get rid of the denominator. The denominator is x, so I multiply through by the LCD, which in this case would be x. So let's multiply. Actually, I'm multiplying both sides of the equation by x, but on the left side, when we multiply, that means that I multiply each of the terms by x. So in this first term, x divided by x equals 1, so I'm left with 1 times 3 minus 1 times x equals 0 times x. How about if we add x to both sides to isolate the x, since it is a linear equation? We'll get 3 equals x. Now, one thing I need to check, I've sort of messed up this equation. This equation was 3x minus 1 equals 0. I've got to make sure that this 3 does not make this denominator equal to 0. Remember that any time that we multiply both sides of an equation by a variable factor, we can introduce extraneous solutions, and those would be solutions that make the denominator equal to 0. If x is equal to 3, does this denominator equal to 0? No, it does not, does it? We would have 3 over 3 minus 1 equals 0. Well, of course, 3 divided by 3 is 1. 1 minus 1 is 0, and we have just checked that problem, haven't we? So x equals to 3 would be a solution. Secondly, let's work on this second equation. Once again, let's rewrite this x to the minus 1. That would be 1 over x minus 2 equals 0. Once again, I need to get rid of the denominator. Anytime that we have variables in the denominator, one of the first things we do is to get rid of them. We get rid of them by multiplying by the LCD. Once again, my LCD is x, so let's multiply both sides of the equation by x. In the first term, x divided by x is 1, so I have 1 times 1 or 1 minus, in the second term I get 2x, and on the right side I get a 0. Once again, let's add the 2x to both sides. I have a linear equation, so I want to isolate the x, so I'll have 1 equals, of course, minus 2x plus 2x is 0x, and 0 plus 2x gives me 2x. Last, I need to divide both sides by the 2 to isolate the x. So I get 1/2 equals x. Now once again, I multiply both sides of this equation by the variable factor x, so I've got to be sure that 1/2 is not extraneous. Let's take this equation that I had before I multiplied both sides of the equation by x. It was 1 over x minus 2 equals 0. If I replace this denominator with 1/2, I'll have 1 over 1/2 minus 2. Actually, the question is, does it equal to 0? I can completely check this. I will leave the check to you. I'm not going to completely check it, but I do need to make sure that this denominator is not 0 when x is 1/2, and it's not. It's equal to 1/2. So the solutions for this equation are x equals 3 and x equals 1/2. I will leave the actual check to you. I'm going to write this in solution set notation. I would caution you, though, Remember what this really means is 3x to the negative second means 3 over x squared. Remember that I may write it this way because the 3 is a factor and x to the negative second is a factor. And once again, this negative 2 power does not apply to the 3. So the x to the negative second can be rewritten as x squared in the denominator. And of course, the 3 stays in the numerator. For this second term, I'll have 7 over x plus 2 equals 0. Of course, I have checked to make sure that 3 1/2 were not extraneous solutions from in the equations that I solve to actually find them, which in case we've forgotten, it would be this equation and this equation. I checked the 1/2 here and I checked the 3 right there. But I just always caution you when you are working with these equations with the negative powers that those negative powers on those variable factors, put those variables in the denominator and just be real careful that you make sure your solutions do not make either of these original denominators 0 either. And in this case, the 3 would give us 3 squared or 9 here and a 3 there, so we don't have zeros using 3. And the 1/2 would give us 1/2 squared here, which is 1/4, and a 1/2 for this denominator. So just be sure you check your fractional equations to make sure that none of your solutions make the denominators equal to 0. Now, let's look at problem number 4. This will be the last problem that's in an equation in quadratic form. Let's just check real quick. Let's take this x to the 1/3 and square it. And sure enough, power of a power tells us to multiply these powers, and 1/3 times 2 gives us 2/3. So when we square this x to the 1/3, we get the variable expression in the first term, x to the 2/3. What is important about that for us to understand is that this x to the 2/3 means x to the 1/3 squared, and x to the 1/3 squared could be written as x to the 1/3 times x to the 1/3, which represents a factorization for this first term, but also that one of these factors represents the variable expression of that middle term. So I may begin by saying x to the 1/3 times x to the 1/3, and now to get the terms, the second terms in my factors, I will go to the positive 3. Since it's positive, I know that my factors will have the same sign. This middle term tells me that they will both be positive, and I want the factors of 3 whose sum is 4. Well, that would be plus 1 and plus 3, wouldn't it? Now, let's set each factor equal to 0 using our zero product theorem. And then let's solve. Let's remember that x to the 1/3 means the cube root of x. Once again, we need to eliminate this radical, and to do so, we want to isolate the radical term. Let's subtract 1. And now let's cube both sides. Of course, the cube root of x cubed is x, and negative 1 cubed is negative 1. For this second equation, let's write the x to the 1/3 as the cube root of x. Let's subtract 3 from both sides. Let's cube both sides. And the cube root of x cubed is x, and negative 3 cubed is negative 27. Now when we raise both sides of an equation to odd powers, we don't have to worry about introducing extraneous solutions. Let's write the solution set, -1, -27, and I will leave the check of these solutions to you. Of course, I hope that you realize that all equations in quadratic form do not factor, just like all quadratic equations cannot be factored to solve. If they cannot be factored, then of course we have to use other methods. You will learn these other methods in other math courses. Now, what I'd like for us to look at is what we call higher degree equations, and I'd like for us to solve them by factoring. When we factor these higher degree equations, our technique for factoring is grouping. So I'd like for us to review how we factor by grouping. To begin with, do you remember what tells us to try to factor something by grouping? If we have 4 or more terms, then we consider grouping the terms to factor. So let's review how we factor by grouping, and then let's look at some problems where we will solve them by factoring by grouping. Factoring by grouping. First, we group the first 2 terms together and remove their common factor. Also, group the last 2 terms together and remove their common factor. Determine whether or not a common binomial factor has been generated. If it has, and that's what we're trying to do by grouping these first 2 terms and taking out a common factor, and grouping these second 2 terms and taking out a common factor, we want to generate a common binomial factor, and if we do, we can remove the common binomial factor. However, if a common binomial factor has not been generated, we reorder the polynomial and we repeat the process. After we have one side of an equation completely factored and the other side of the equation equal to 0, we may extend the zero product theorem and set each factor equal to 0 to find the solutions of the equation. Let's look at problem number 5. Our instructions say use factoring by grouping to solve. Our equation is x cubed minus 4x squared plus 25x minus 100 equals 0. Let's first discuss why we call this a higher degree equation. Notice we have the quadratic term, a linear term, and a constant term. This is not a quadratic equation though, because we also have the x cubed term. When we have a term and the power of x is greater than 2, we call this a higher degree equation. If we have any terms where x is raised to a whole number power greater than 2, we call it a higher degree equation. I would suggest whenever you solve higher degree equations that you get all the terms on one side of the equation and 0 on the other side of the equation. Then we try to factor the left side of the equation. Because the left side of this equation has 4 terms, that would suggest to us to factor by grouping. When I factor by grouping, usually I simply group the first two and then group the second two. When we factor by grouping, we look for a common factor. Of course, we should always look for a common factor in all four terms first, but we don't have a common factor in all four terms here. So we will simply group the first two and the last two. In the first two, we can common factor x squared out of both terms. In the first term, that leaves us with x. In the second term, that leaves us with a negative 4. Looking at the next two terms, we have a common factor of 25. Of course, sometimes we take out a positive 25 and sometimes we take out a negative 25. We want to take out either a positive or negative so that what's left in our parentheses for our first term of our binomial is a positive x. So should we factor out a positive 25 or a negative 25? We should take out a positive 25, shouldn't we? Once we decide that we're going to take the positive 25 out, we factor the positive 25 out of both of these terms. When I factor a positive 25 out of the 25x, I'm left with x, and out of a negative 100, I'm left with negative 4. Remember, when we common factor, what we really do is we take our original term and we divide it by what we're factoring out, and we write here what's left. 25x divided by 25 leaves us with x. Negative 100 divided by 25 leaves us with negative 4. Of course, to complete the equation, we have equals 0. Now, although I have factored to get from this step to this step, the left side of this equation is not considered in factored form. Remember, to be in factored form, we have to have a product of the factors. This is not a product. We have one term that is a product plus another term that is a product. This is still a sum because we are taking this first term and adding the second term to it. We need to look at our terms. We have two terms here. Once again, we look for a common factor. This time we're hoping for a common binomial factor. And notice, we have this common factor, x minus 4. This term means x squared times x minus 4. So we have a common binomial factor of x minus 4 for both of these terms. In the second term, this means 25 times x minus 4. So now, from these two terms, let's factor out our common factor, x minus 4, and let's write what we're left with. In this first term, what do we multiply x minus 4 by to get x squared times x minus 4? Well, obviously, it's x squared. And in this second term, what do we multiply x minus 4 by to get 25 times x minus 4? Well, obviously, it is a positive 25. Remember that if we multiply back, we should be able to get this. And x minus 4 times x squared gives us x squared times x minus 4. And x minus 4 times 25 gives us 25 times x minus 4. Now, the left side of this equation is in factored form. It represents a product. A product of the binomial factor x minus 4 times the binomial factor x squared plus 25. The question is, for these factors, are they both completely factored? Are they both prime factors? Well, x minus 4 is a prime factor, and x squared plus 25 is the sum of squares, and we know that we don't factor the sum of squares. So yes, this is completely factored. Now we may use our zero product theorem and set each of these factors equal to 0. The zero product theorem says that if I have one factor times another factor, and that is equal to 0, that either the x minus 4 equals 0 or the x squared plus 25 equals 0. Our first equation is a linear equation. This second equation is quadratic. We should be able to solve any linear or quadratic equation we come to, shouldn't we? So let's work on this first linear equation. We know we want to isolate x. We do that by adding 4 to both sides. We get x equals 4 as an equivalent equation. On x squared plus 25, it's quadratic. It doesn't factor. You could use the quadratic formula on it, but since it's missing the x to the first power term, usually when I'm missing that linear term, I solve for x squared and then extract roots. Solving for x squared means to get x squared by itself. To do that, I need to subtract 25 from both sides of the equation. I get x squared equals negative 25. Using my extraction of roots property, I know that my x solutions are equal to plus or minus the square root of the negative 25. And of course we know that the square root of negative 25 is 5i. Let's write our solutions in set notation. We have 4 and then we have plus or minus 5i. So our three solutions for this equation would be 4, 5i, and minus 5i. I will leave the check of these solutions to you. Problem number 6 is also a higher degree equation to solve. Notice that we have the left side equal to 0 on the right side. We will try to factor it. Since we have 4 terms on the left, we will try factoring by grouping. Let's group these first 2 and then these last 2. Let's take a common factor out of these first 2. That would be 9x squared. When I factor 9x squared from 9x cubed, I'll have x. When I factor 9x squared from a negative 27x squared, I'll have negative 3. Now remember, if this is the binomial factor I get from common factoring these first 2 terms, that's the same binomial factor I want when I common factor these second 2 terms. Look at these 2 terms. The only common factor would be a positive 1 or a negative 1. So I need to decide whether to factor out a positive 1 or a negative 1. And notice what I want left. I want x minus 3 as my common binomial factor. So when I look at this first term, negative x, should I factor a positive 1 or a negative 1 out so that I am left with a positive x? I should factor the negative 1 out, shouldn't I? When I factor negative 1 from negative x, I am left with a positive x. And when I factor a negative 1 out of a positive 3, I am left with a negative 3. Notice my signs. I have a positive x minus 3 for a common binomial factor. And check it, my students seem to have a lot of trouble with these signs. We should be able to multiply back through and get these 2 terms. Negative 1 times x gives us negative x, and negative 1 times negative 3 gives us positive 3. If you'll remember, if you factor a negative out of terms, then what happens to those terms is that the signs are the opposite of what they were before you factored the negative 1 out. So this was a negative x. When I factor a negative 1 out of it, I'm left with a positive x. This is a positive 3. When I factor a negative 1 out of it, I'm left with negative 3. Now, once again, yes, I did factor from this step to this step, but is the left side of this equation in factored form? Is it a product? It is a difference, isn't it? This is subtract. This means this term subtract this term. To get this in factored form, once again, I'll look for common factors, and I have a common binomial factor of x minus 3. So let's factor that x minus 3 out of each of those terms. In this first term, we're left with 9x squared. In the second term, we're left with minus 1. And then we have equals 0. So the left side of this equation is now a product. It is now in factored form. The question is each factor a prime factor? Can I factor either of these factors anymore? Well, x minus 3 is a prime factor. But what about 9x squared minus 1? It's the difference of squares, isn't it? So I can factor the 9x squared minus 1. Remember, when we factor the difference of squares, our first terms and our factors would be what we squared to get 9x squared, and of course that would be 3x, wouldn't it? And of course we have a positive sign and we have a negative sign. We have opposite signs, and then of course the second term should be what we squared to get 1, and of course that is 1, isn't it? Now, are my factors prime? Well, 3x plus 1 is prime, and 3x minus 1 is prime. So I have taken the left side of this equation and I have it factored into prime factors. Now, this time I have 3 factors, but because they equal to 0, I can extend my zero product theorem and say if this factor times this factor times this factor is equal to 0, the only way that can happen would be for one of these to equal to 0. So my zero product theorem says that either x minus 3 equals 0 or 3x plus 1 equals 0 or 3x minus 1 equals 0. These all 3 are linear equations. Let's solve them. Let's add 3 to both sides of this equation to isolate x. We get the equivalent equation x equals 3. Let's subtract 1 from both sides of this equation. Then let's divide by 3, and we'll get x equals negative 1/3. And let's add 1 to both sides of this equation. Let's divide both sides by 3, and we'll get x equals 1/3. Let's write our solutions using solution set notation. We'll have a 3, then we have a negative 1/3 and a positive 1/3. Let's write that as positive or negative 1/3. I will leave the check to you. Let's look at problem number 7. You'll notice that we have an x to the 4th power term in this higher degree equation. Once again, we are instructed to solve. We will factor by grouping. Notice our x to the 4th power term and an x cubed term, both those terms make this equation a higher degree equation. Notice we have our terms on the left set equal to 0 on the right. Of course, we try to factor. We'll look for a common factor first in all 4 of these terms, and there's not a common factor for all 4 of these terms, but since there are 4 terms, that tells us we want to group Let's start first with these first two terms and then these last two terms. In these first two terms, the common factor would be x squared. Let's try that again. How about x cubed? When we factor x cubed out of the first term, we're left with 5x. And when we factor x cubed out of a negative x cubed, we're left with minus 1. Moving on to the last two terms, the common factor is 8. Should we take out a positive 8 or a negative 8? Well, we want to factor it out of 40x so that we're left with the positive 5x, and out of negative 8 so we're left with the negative 1. We need to take a positive 8 out of this 40x so that we're left with the positive 5x, right? 40x divided by 8 would leave us with 5x, and negative 8 divided by 8 would leave us with negative 1. Of course, on the left, we still have a sum. We want a product, so we can use our zero product factor theorem. We have two terms on the left. The common binomial factor is 5x minus 1. Let's factor the 5x minus 1 out of each term. In the first term, we're left with x cubed. In the second term, we're left with plus 8 equals 0. Now, on the left, we do have a product. The left side of the equation is in factored form. Are the factors prime factors? Well, 5x minus 1 is. What about x cubed plus 8? Can that be factored? Well, this is a binomial factor. It is a sum. It is a sum of cubes, isn't it? Let's rewrite that. Of course, we know we cubed x to get x cubed. What did we cube to get 8? We could think of that as 2 cubed, couldn't we? A sum because it's addition, and then we have 2 cubes for our terms. So how do we factor the sum of cubes? We know that we will have a 2-term factor and a 3-term factor. Let's write the 2-term factor first. For our first term in the 2-term factor, what did we cube to get x cubed? X. So that is our first term. Use the same sign. Since it's a sum, we want to use a plus. What did we cube to get 8? We cubed 2. So the terms of our binomial factor would be x plus 2. Let's use this x plus 2 to generate our trinomial factor. The first term would be this x squared. Remember, the sign of the second term is the opposite of the sign between the two terms in our first factor. Since our first factor has a plus sign, we know we'll use a negative sign. What we do to get this term is to take the 2 and multiply it times the x. That gives us 2x. Remember that the third term is always positive, and to get it, we square the second term in this first factor. 2 squared is 4. So let's check our factors now. On the left side, we still have a product. We have 3 factors now. Of course, 5x minus 1 is still prime. X plus 2 is prime. Is x squared minus 2x plus 4? Can we factor this trinomial? Well, of course, to factor it, since the leading coefficient of x squared is 1, we know that if it factors, that the second terms of the factors have to be factors of a positive 4. We need to be able to add them to get a negative 2. Well, of course, since it is a positive 4, we know the factors will have to have the same sign. And since the middle term is negative, we know they'll have to be negative. The consideration here would be negative 1 times negative 4. If we add negative 1 and negative 4, we get a negative 5, not a negative 2. The other consideration here would be negative 2 times negative 2. If we add negative 2 to negative 2, we get negative 4, not negative 2. So this trinomial is a prime factor. Now we may extend our zero product theorem. If we have this factor times this factor times this factor equals 0, then we know that either the 5x minus 1 equals 0, or the x plus 2 equals 0, or the x squared minus 2x plus 4 equals 0. We have three equations. These first two are linear, and the third one is quadratic. So let's work on solving these three equations. For our first linear equation, we want to isolate x. Let's add 1 to both sides. Let's divide by 5. We get an equivalent equation, x equals 1/5. For our second linear equation, let's subtract 2 from both sides. We get an equivalent equation, x equals negative 2. And for our quadratic equation, we know that the left side doesn't factor. We've already considered that. We have three terms on the left side. That would suggest that to solve, since it doesn't factor, we would either want to complete the square or use the quadratic formula. I'll use the quadratic formula. It's already in standard form, so I know that a equals the coefficient of my x squared term, which in this case is an understood 1. B equals the coefficient of my x term, which is negative 2. And C equals my constant, which is 4. Now remember that for my quadratic equation, to use my formula, that my x solutions equal minus b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So let's replace my a, b, and c in this formula with my a, b, and c. Of course, the a, b, and c are found when the equation's in standard form, and we've already done that. So we would have minus b, that would be minus, our b is a negative 2, plus or minus the square root of our b squared, minus 4 times a, which is 1, times c, which is 4, divided by 2 times a, which is 1. Of course, minus a minus would give us a positive 2, plus or minus. We know that when we simplify this radical, that we follow our rules of order, which say to square first, and then we may multiply. Negative 2 squared is positive 4. Subtract 4 times 1 times 4 is 16, all over our denominator of 2. We'll have 2 plus or minus. Now we combine these numbers before we simplify our radical. 4 subtract 16 is negative 12, all over 2. Let's simplify the square root of negative 12. We'll think that the square root of negative 12 equals the square root of negative 4 times the square root of 3. The square root of negative 4 we know is 2i, and the square root of 3 is irrational. Now we want to reduce our fraction. We have simplified that radical. Can we reduce the fraction? Well, do we have a common factor? Well, remember that this numerator is two separate terms. We have a common factor of 2, don't we? And since the denominator has a factor of 2, we do have a common factor. Let's factor out the 2 in the numerator. In the first term, it leaves us with 1, plus or minus. In the second term, when we factor out 2 from 2 times I times the square root of 3, we're left with I times the square root of 3 all over 2. We may now divide our common factors, and we are left with 1 plus or minus I times the square root of 3. Now, of course, this represents two different solutions, 1 plus I times the square root of 3 and 1 minus I times the square root of 3. Now, let's go back and get our solutions for, let's see, we have 1/5, -2, and then, of course, plus or minus I times the square root of 3. So here is our original equation, and let's write all the solutions that we have found using solution set notation. 1/5, -2, and then let's write 1 plus or minus I times the square root of 3. I will leave the check of these solutions to you. For problem number 8, we also have a higher degree equation. Our higher degree terms would be x to the 5th and x to the 4th. We know that we want all the terms on the left and 0 on the right so that we can factor, if possible. And once again, because we have 4 terms on the left, that suggests factoring by grouping. Of course, always when we start to factor, we check to see if we have a common factor in all of our terms. So looking at all 4 of these terms, we don't have a common factor, of course, other than 1 or -1. So moving on, let's group these first 2 and these last 2. What's our common factor for these first 2? X to the 4th, isn't it? When we factor x to the 4th out of x to the 5th, we're left with x, and when we factor x to the 4th out of a positive 2x to the 4th, we're left with a positive 2. For our last 2 terms, we have a common factor of 16. Should we take out positive 16 or negative 16? We need a positive x for the first term of that common binomial factor, so what should we take out? Negative 16, shouldn't we? When we factor negative 16 out of negative 16x, we're left with x. And when we factor negative 16 out of negative 32, we're left with positive 2. Once again, remember, if we take a negative out, the signs of what's left in the parentheses should be the opposite of what we had to begin with. Our signs initially were negative here, and now notice they're both positive. Now, of course, this is a difference. It's not a product yet, is it? It's not considered to be in factored form. We have this term subtract this term, so we look for a common binomial factor, and of course x plus 2 is the common binomial factor. Let's factor that x plus 2 out of each of these terms. When I factor it out of this first term, I'm left with x to the 4th. When I factor it out of this second term, I'm left with a minus 16. The left side of the equation is factored. It is in product form. Are my factors prime? Well, x plus 2 is prime. Is x to the 4th minus 16 prime? Can I factor x to the 4th minus 16? I can, can't I? It is the difference of squares, isn't it? So I know it factors. I know that these signs are opposites. I know that my first terms are what I squared to get x to the 4th, and of course we square x squared to get x to the 4th. And my second terms are what I squared to get 16, and that would be 4. The left side, of course, is in factored form, and once again the question is, are all my factors prime? Well, x plus 2 is prime. What about x squared plus 4? That's the sum of squares, isn't it? So it's prime. What about x squared minus 4? Well, that's the difference of squares, so I can factor that. Well, let's write our prime x plus 2 and our prime x squared plus 4, and then let's factor this difference of squares. Of course, it factors into two factors, opposite signs. What do I square to get x squared? X. What do I square to get 4? 2. Now, what about my factors on the left? Are they all prime? Well, the x plus 2 and x minus 2 are prime. So I now have 4 prime factors. Notice that these two are the same. Now, my zero product theorem says that I can set each of these factors equal to 0. So, I will have x plus 2 equals 0, or x squared plus 4 equals 0, or, now do I really need to write this one again, x plus 2 equals 0? Isn't the solution for this equation the solution for this equation because they're the same equation? I don't really need to write that, do I? Now for these 4 equations, 3 of them are linear and 1 is quadratic. Let's solve. For this first one, let's isolate the x by subtracting 2 from both sides. For this second one, it is quadratic. I have the quadratic term and I have the constant. I am missing the linear term, so I will choose to extract roots. To extract roots, I want to isolate the x squared. To isolate the x squared, I want to subtract 4 from both sides. I get x squared equals negative 4. My extraction of roots property says that my x solutions will equal plus or minus the square root of negative 4. Of course, the square root of negative 4 is 2i. So I'll get my x solutions equal plus or minus 2i. Of course, my solution here is negative 2, just like this first equation. For this last equation, it's linear. Isolate the x by adding 2 to both sides, and I get x equals 2. Let's write these solutions in solution set notation. I have negative 2. I have plus or minus 2i. I do not need to write the negative 2 again. I have positive 2. Whenever we have a solution that we get twice because we have 2 of the same factor, we say that that solution, or sometimes we call a solution a root, is of multiplicity of 2. And that just means that it was generated from 2 of the same factor. Now, I would like to check one of these. I know I haven't checked any of the equations in the higher degree equation section of this lesson, so I would like to check one of these just so you realize that you can check it. I think the one that I will choose to check will be x equals negative 2i. We haven't had a lot of experience in raising these non-real numbers to power, so I thought that it might be helpful to do that. So of course, if I'm going to check, I replace each of these x's with negative 2i. Since x is to the 5th power, I'll have negative 2i raised to the 5th power plus 2 times negative 2i raised to the 4th power minus 16 times negative 2i minus 32, and the question is, does that equal to 0? So when I calculate these values on the left side, I should get 0. Well, of course we know order of operations says to compute our powers first. Since I have a product, since I have factors in these parentheses, I know that when I raise a product to a power, remember a times b to the n, then I apply that power to both the factors. So I will have negative 2 to the fifth times I to the fifth plus 2 times negative 2 to the fourth times I to the fourth. We'll hold on the multiplication until we have completed raising our powers. Negative 2 to the fifth would be negative 32. I to the fifth is actually considered to be I to the fourth times I. What is I to the fourth? It's positive 1, isn't it? So I to the fifth would mean 1 times I, which of course is I. Let's see, we'll have plus 2, negative 2 to the fourth is positive 16. I to the fourth is I to the fourth, which is 1. Now I think we have completed raising everything to its powers. Let's do our multiplication. This first term is negative 32i. This second term is 2 times 16 times 1, which is 32. For this third term, minus 16 times minus 2i would be plus 32i. And then, of course, this last term is negative 32. And the question is, does this equal to 0? And what happens? Minus 32i plus 32i adds to 0i, which is 0. 32 minus 32 adds to 0. So sure enough, we get 0 equals 0. So x equals negative 2i. Checks. Once again, let's make sure that we realize that for this equation, this is my solution set. I will leave the check of the other solutions to you. In case you're wondering on problem number 8, if we could write the negative 2 and positive 2 together on that solution set notation, we can. How about if we look at that one more time? Certainly we could take this and write the minus 2 and the plus 2 as plus or minus 2. And then of course we will have plus or minus 2i. This solution set notation would mean the same thing as that solution set notation and would represent the same solutions. When you get ready to solve a higher degree equation, be sure that you put all of your terms on one side of the equation and 0 on the other side of the equation. If you have 4 or more terms, factor by grouping. Once you get one side of the equation factored, since you have 0 on the other side of the equation, you may use the zero product theorem and set each factor equal to 0 and then solve the resulting equations. This completes the solving equations in quadratic form and higher degree equations by factoring. Please rewind the tape before you return it. Thank you.